Now, for number 4, we have two concepts, fixed cost and fixed benefit. For number 4, I will be dividing my discussion into two. Let me discuss first fixed cost. Now, if you understand fixed cost, hopefully it will be easier for us to understand fixed benefit eventually. Because technically, fixed benefit is just the opposite of fixed cost. Okay? Now, let me give you the base example for fixed cost. Let's say you are riding the MRT, and let me give you the MRT ticket cost function. Okay? Let's say when you ride the MRT, if you decide to ride the MRT, let's say you have to pay some fixed cost of 9 pesos plus 50 cents for every station that you pass through. Okay? So if from point A to point B, you will pass through 10 stations, then your ticket cost is 9 plus 0.5 times 10, that's 5. So 9 plus 5 is equal to 14. Okay? And your ticket cost is 9 plus 0.5x if you are riding the MRT. And mathematically, you are riding the MRT if x is positive. However, if you are not riding the MRT, and let's say you're taking some other form of transportation, then obviously your MRT ticket cost is 0. Now, how do we now use the concept of an on-off switch in order to linearize this MRT ticket cost function? What do we have to turn on and off in this case? Let me give you an idea. We will let a binary variable, in this case, be equal to 1 or 0. 1 if x is positive, 0 if x is equal to 0. And because y equals 1 if x is greater than 0, then technically your MRT ticket cost can now be equal to 9, the fixed cost, but you multiply the switch, okay, and you add 0.5x. And this function 9y plus 0.5x works even if x equals 0. Why? Because if x equals 0, then technically by definition, because we defined y to be 1 if x is positive, 0 if x equals 0, therefore if x equals 0, then y should be 0, and therefore your MRT cost is 0. On the other hand, if you are riding the MRT, then you have some value for x, and because of this definition, y is equal to 1. Therefore, you have this MRT ticket cost. Now, it might seem simple that the linearization of this MRT ticket cost function, the split function, is just this, by adding this definition of y. However, we have to understand that y here is a dependent variable. And if a variable is dependent, and in this case y is dependent on the value of x, and as you try to understand, the value of y is dependent because if x is positive, the value of y is 1. If x is 0, the value of y is 0. And as you can see, y is dependent. And if y is a dependent variable, then there should be a constraint in your model that will try to replicate or represent this definition. What do I mean by that? So let me add a constraint. What is the constraint? If I add x less than or equal to my, this constraint will represent this definition. Let me explain. Let's look at scenarios. What will happen if x is positive? Let's say x is 2. Let's say. If x is equal to 2, and remember, we have the binary constraint y is between 1 and 0, and integer. Okay? So if x is equal to 2, so this is equal to 2, what will be the possible values of y so that this constraint is valid? So 2 is less than or equal to m times some variable, and this variable can be either 1 or 0. The only possible value for y if x equals 2 is if y equals 1. In fact, if you try to substitute x with any positive value, so imagine x equals 3 or x equals 1, the only possible value for y is 1. On the other hand, look at what will happen if x equals 0. If x equals 0, then this is 0. Now try to imagine what are the possible values of y. If y is 1, then 0 less than or equal to m is valid. Okay? Is valid. However, if you also look at the possibility that y equals 0, so if y equals 0, so x equals 0, 0 is less than or equal to 0, that's also valid. Correct? So technically, if x is equal to 0, then y can be either 1 or 0. Which means, looking at our definition of y, it is actually missing some elements. What are the missing elements? If x is equal to 0, your y can be either 0 or 1. However, this is not our original intent for y, because our original intent for y is if x is equal to 0, then y should be equal to 0. Now, let me explain this in two ways. First, if you have a scenario where if x equals 0, y can either be 0 or 1, and because y, the binary variable, is attached to a positive constant 9, and this positive constant 9 is part of a ticket cost where we'd like to minimize eventually. So if you are allowing y to be 1 or 0, if x is equal to 0, then generally speaking, the model will normally choose 0. That's usually the easier way to explain this. However, to explain this in a much better fashion, and so that you will eventually understand fixed benefit, let me now explain to you the concept of mortal sin. Now, to explain the concept of mortal sin, let me now redefine the definition of our binary variable y. So we still have our original problem, the MRT ticket cost problem, which is non-linear because it is defined to be a split function. Okay? Now, we will define y to be equal to still a split function 1 if x is positive. So what does this mean? If you write the MRT, y, or the binary variable which we will attach to the fixed cost, should be 1. However, if you don't write the MRT, imagine this, if you don't write the MRT, you can technically pay the fixed cost, right? However, you can also opt not to pay the fixed cost. So technically, if x equals 0, meaning you don't write the MRT, you may pay the fixed cost or you may not pay the fixed cost. However, if you write the MRT, it is a mortal sin not to pay the fixed cost. Therefore, the only option for writing the MRT is for you to pay the fixed cost. So if you see the difference, the way we defined y a while ago is this: y is equal to 1 if x is positive, and 0 if x equals 0. So as you can see, there's a very, very big difference. This does not show the mortal sin. This actually shows the mortal sin. Where? Here. Because you actually erased the option of letting y be equal to 0 if x is greater than 0. Why? Because this is where the mortal sin exists. Okay? And because you erased this, and because you erased this part, therefore, the constraint that we added before, if you remember, this is x less than or equal to my, will work. Why? Because if x is positive, look, if x is positive, then y is forced to be 1. However, if x equals 0, if this is 0, then y can be 1 because 0 is less than or equal to m, or y equals 0 because 0 is less than or equal to 0. And that is how we try to understand the concept of mortal sin, and why defining your binary variable in a way to show mortal sin will actually help you understand this constraint that is added. Hopefully now you've understand the concept of mortal sin. And let me now explain the concept of fixed benefit using mortal sin. Now let's say for operations research, instead of giving you a long test, let's say I will require you some paper. So OR paper grade. And let's say the way I will grade this paper will be based on the number of pages that you will submit. So again, I will define the OR paper grade to be a split function. And if x in this case is the number of pages you submit, if you are submitting something, and therefore that means x is greater than or equal to greater than 0, then let's say I will give you a bonus of 9 points, and for every page that you submit, you will get 0.5 points. However, if you don't submit anything, meaning x equals 0, then I hope it's very obvious that you will not get anything. Now, our goal right now is again to linearize this split function by defining y, a binary variable, in this case, 1 and 0, and 1 if x is positive, and 0 if x equals 0. Now, it is at this point where I'd like to introduce again the concept of mortal sin. And let's try to understand. Where does the mortal sin exist in this scenario? Now, given that the function is an OR paper grade, and therefore this split function is some benefit, if you submit something, it is technically possible that you don't ask for the bonus. Again, if you submit something, it is very possible that you don't ask for the bonus. But of course, it is also possible that you ask for the bonus. Remember, y will be attached to the bonus score of 9. Okay? Now, if you didn't submit anything, it is a mortal sin. It is a mortal sin to let y be equal to 1 if x is equal to 0. And therefore, I hope it is clear that the complete definition of y, which is a binary variable, is equal to 1 or 0 if x is positive, or meaning if you submitted something. However, y is strictly 0 if you didn't submit anything. And therefore, given this definition of y, our OR paper grade, so grade, will now be equal to 9y plus 0.5x. Again, because y is a dependent variable and the value of y depends on the value of the variable x. Therefore, we need a constraint. And what constraint is that? So we will add subject to, and we will be adding an mx greater than or equal to y. What is m? As always, is our very big number, and x is the variable x, which represents the number of pages submitted, and y is the binary variable that will control the bonus. Okay, so let's try to understand. If x is positive, so if x is positive here, what will happen is the left-hand side will be some positive number. And because the left-hand side will be some positive number, and the constraint is a greater than or equal to y, and remember y is binary, therefore, if this is positive and this is binary, that means y can be actually either 0 or 1. Okay? Which supports this definition. On the other hand, what will happen if x is equal to 0? If x is equal to 0, then the left-hand side becomes 0. This becomes y less than or equal to 0. And because you have this part of the constraint of your non-negativity, so you have y less than or equal to 0, y greater than or equal to 0, you get the intersection, you get y is strictly equal to 0. So I hope by learning the concept of mortal sin and by defining your y in a way that will show the mortal sin, it will be easy for you to understand why the constraint mx greater than or equal to y is the constraint that we need in order to fulfill this definition of the binary variable.